that's an explanation from a technician in Italy about the telescopes and the milling. Steiger in 1924 thought to create a milling on the tooth, a preparation on the inside of the tooth, and he thought the clasp that would go on the labial side is very anesthetic. So this is the clasp on the inside of the mouth. And when Steiger thought about doing this, you had to prepare it perfectly at 0 degrees, which is extremely difficult. But Steiger thought that he could create like a small metal part that will friction there, that will be a little bit elastic, that will be soldered there, and when it loses elasticity, you can reactivate it by pressing it a little bit to the outside. So this is how he thought doing it. During the years, people have thought, why don't we create a crown and place such a thing on the distal of a crown? This is an extra coronal attachment. It has 2 sliding guides. Another type of crown can be done like this, and obviously this type of crowns is done under parallelometer to have it absolutely perfectly in parallel, because the dentist could do that, but it's extremely difficult. Only with the template guided vector technique you could do such preparations directly into the mouth. But here you have two clasps that create a friction, and they will sit on the tooth. And now what we see here is a telescope. This is the classical telescope, which means the primary crown that looks like this. In the beginning it had those 2 sliding guides. Okay, and then the crown, the final crown, would sit, sustaining the denture, would sit on that primary crown. Now let's see how this is done, how they look. See, this is a denture. There's 2 arms clasp on a milling. The milling is quite simple. See, and those are the 2 arms. You see the sliding guides, you see that everything is cast in one piece. Now, this is an extracoronal system. This is made by the dental technician himself. And on the inside of it, you see these two let's say tongues of metal that can be activated, you see. They are soldered in the tip and they can be activated. Now this is very difficult to produce, obviously. So nowadays we don't do that anymore. It's just to understand historically how things evolved. So the teeth are united, I mean the crowns are connected. This is the milling, Steiger's milling, right, on the inside. But again, the crowns are done like that, not the tooth directly. You see, those are the friction devices. You can bend them a little bit in order to increase the friction, right? To have the denture sit on position. It's very complicated anyhow to do this, and that's why it's also expensive. Here we have a telescope denture, telescopic denture. The dentist can remove it from the mouth of the patient. And if we look one tooth, a single tooth, this is the telescope. Primary coping. This is extremely sophisticated. You see there's two retention devices on each sliding guide. See those devices that are soldered at the top of the crown, at the incisal aspect of the inside of the crown. Yeah, this is really complicated. But just to see how it works. So it ensures the friction all the way. So this is done by milling machines, but manual milling machines. Of course, automatic milling machines can do the same. This is overdenture, right? Like 3 implants on one side, 2 implants on the other side. Those bars are screwed on the implants, right? The dentist can remove those things if this is needed to clean under the bars, to clean the implants. Okay, but the patient can remove the denture because the denture clicks on those 2 bars. Right? It's highly hygienic for the patient. Right? The dentist can unscrew that and clean perfectly the implants, and this is the overdenture that goes over it. You see, it does click there. There is some attachments inside the denture. As you can see, again, this is a metal pin that can be bended in order to increase the friction. So this is how this overdenture is made. Now let's see how such a milling is done manually with a milling machine, but done manually. A double arms milling, like the one that we've seen before, like this one that we're seeing now. So how do you do this? Those are the 2 pins, mesial, which can be bent, and the distal, which is fixed. That's how you insert it. And let's see how you build this. How you build such a system. So first, you use your parallelometer, okay, to determine the axis of insertion. This is just the analysis. You see, there's not a burr there. It's just a metal pin, very fine, soft, smooth metal pin, just to make sure that the insertion axis of the denture is the right one, that there is no undercuts. And then you block this model in position. You see, when you are okay with the angle of the model, you block it, and you say, okay, this is how I shall do it. Here, just to make it faster, the wax crowns have been already modeled. This is a special wax that allows the milling machine to mill in it. Okay, it will not melt quickly, it melts very late. So this is the crowns that have been modeled. Of course, they will be turned into metal ceramic crowns, but here we have the full modeling because we want to have a clear idea of the anatomy of the final crown. Okay, so part of the final crown will be fixed, as we see there. Part of it will be the removable side. Okay, so now this is the parallelometer, which is actually a parallelometer with a motor. That is a manual milling machine. And now you see that there's air being blown there to cool down the wax. The rotation of the micromotor is around 3,000 rotations per minute. And air is used, you see. And this is the special wax that allows you to to do the milling of the wax. The burr is 1 millimeter diameter. Look at the tip of the burr. The movement is done according to the rotation direction of the burr. And so we try to create a shoulder at that level, right? We get to the middle of the cusp. We increase a little bit the thickness. I mean, remove more wax because we want the clasp to be thicker a little bit. So the wax is, as you see, is taken away by the burr. The burr turns in such a direction so as to remove the wax, not bring it upon the rest of the wax, right? Around 3000 RPM, as we said, and this is how you prepare it in wax. You are sure now that you are 0 degrees, absolutely 0 degrees, right? It's like a spatula, but this is guided at 0 degrees and it's rotating, so it's way easier. So now we create the other interlock, as it is called, or post interlock. This is the best way to call it in English. Okay? So that's how we mill it. Now, what we had to do with milling is finalized. What we need to do is the technician now has to remove an important quantity of wax corresponding to what the ceramic is going to be. So again, double clasp here. This part of the crown will remain fully anatomical. And so now we cast it. This is metal now. We can see that the wax was taken away so as to make space, make room for the ceramic. And now, what do we have to do? We have to see that those two crowns, they are perfectly adapted to the abutments. Later, we'll start to clean and to soften the metal on that side. We do that with special burrs, 1 millimeter, similar to those you use for the wax, but metal burrs for metal. One such burr is the rough one, and then we'll use the soft one, the fine one. So this is rough or coarse, we call it coarse, and the other one is finer, we call it fine, the fine burr. Coarse burr and fine burr. Again with air, because we want to cool everything down. Now the most important thing here is to add some oil. That oil is sprayed on the model upon this maneuver. So it's not very nice, but you have to accept it. It helps a lot while milling if there's oil there. So you see, the movement is against the clock, right? It's exactly the reverse from what we did in wax. The movements should be on small zones. We smoothen the surface. You see, it's almost mirror-like, but it will be even better. the metal has to have at least 250 Vickers strength, bending force, surface toughness. So you have only to you only want to clean everything and to make it smooth. You don't want to remove more than you did in the wax pattern. It's just to make sure there's no bubbles or metal excess or whatever of this kind that will impede the insertion of the clasp and thereby of the denture. So you see it's kind of messy because you see that metal and oil going around, but this is how it is. So the technician goes also into the internal, the mesial interlock, sliding guide, and now the technician is changing the burr into the fine one. The fine burr, the second burr, that you see the yellow ring, which tells you clearly that this is a fine one. There's also the white, which is even finer, but white is the finest, and then comes yellow that the technician is using now. High RPM, that's again like 10,000. So the air is not important now because it's just surface retouch. And you see it also almost looks mirror-like surface. The vertical wall, the shoulder, the interlocks, everything is nicely polished. 8,000 RPM recommended. And now comes back to 3,000 for the final touch with this type of burr. There's the final finishing. And now the technician adds some diamond paste on the burr. Oil and diamond paste. This is a very, very nice substance to polish. And again, everything is 0 degrees, right? Exactly in the axis of insertion. Now, for the final touch, you use some water, cotton, you clean it very well, and this is a mirror-like surface. Now the problem in this case is that you will add ceramic, and when you add ceramic you put everything in the furnace, so you'll have to repolish it again after burning, cooking the ceramic, baking the ceramic on it. But that's how it is, right? You could have placed the ceramic before and done this polishing at the end. It's different possibilities. So again, we showed how this is being constructed. So this is how it looks in the end, in the lab. See, the ceramic is already there.